In this video, I would like to introduce you to a bending element. But before we actually go on to describe a bending element, I thought it would be a good idea to have a little refresher about bending plate theory. Because of course it's a bending element and it's okay to describe the degrees of freedom and where they come from, but it's also more logical to understand where does this element actually fit in, as in what kind of structural requirement would have a bending element. So of course, as I've been telling you, there are certain theories which have limitations and assumptions which can place them in structural environment with limitations. So you have to know what are the limitations related to this particular element as well. So what we are going to consider in terms of bending plate theory is a classical theory of thin plates. And this classical theory of, let me write it down. So we're going to consider classical theory of thin plates, and there are some assumptions that we make so that it can be considered first of all as a thin plate and that the classical theory applies to it. The first one is that the thickness of the plate is much smaller as compared to other dimensions. Yeah, so that means it's supposed to be a thin plate. Second assumption that we make is that the deflections have to be small. So of course then we are always sure that we are within the linear theory. The third assumption is that the mid-plane of this plate, so that means if you're considering the neutral axis of this plate, so the mid-plane of this plate does not undergo any in-plane dimensions, in-plane deformation. Undergo in-plane deformation. So it always remains straight at the midplane or flat at the midplane. And the final one is that the transverse shear deformation is also 0. And that will easily show up again when we describe the strains in the system. So if I want to put everything on a nice picture, yeah, I want to draw a 3D plate, so bear with me here. So this is one part. Of course, I will have another section like this, and of course that makes it a 3D plate. This is just a section of it. So please don't consider that the thickness is not very small as compared to the other dimensions. So I'm only taking a small section. So imagine that the plate is much bigger. And I want to draw it much more clearly, so I'm leaving much more space around it. So if I have a certain load P, which is acting out of plane, yeah. So I have a certain distributed load P, middle acting transversely out of plane upwards. So I have a load P here. Then there is an out of plane load acting on this thin plate. Therefore, we will have some transverse deformation and therefore bending. So what are the stresses that will arise in the system? Say suppose I want to also, let me also draw the coordinate axes. Yeah, if this is X, this is Y, and this is out of plane Z. We always try to take out of plane as Z, always. Then we know that there will be a stress that is acting here in direction X, and you have drawn this diagram many times, so your stress in X direction actually looks like this. It's not a very nice picture. Let me use a thinner pen. And you have stress sigma xx acting like this. Here you also have sigma xy. So of course around the midplane. Then you have sigma xy. Same way here you have yz, and here in this direction you have sigma yy, and you have sigma yz, which is acting over here upwards, sigma yz, and here you have sigma xz, which is acting somewhat like this. Yeah, that's the nature of it. So these are all the different stresses that can act on the system. And the only and if you relate it back to the kind of kind of load that is causing it, you will see that it's all because of some shear forces and some moments that are acting, at every section of this plate. So there are combinations of shear forces and moments that cause these stresses to form. Okay, so that's a general deformation that's happening in this bending behavior in a classical thin plate. Now to derive the stiffness matrix, right, to derive the stiffness matrix, to get to the displacement vector, etc., I need to get also the strain definition of this kind of an element, or for a plate, sorry. So because we are considering everything in terms of plate theory. So if we consider the bending deformation of a very small element, then at any point you have the element that is undergoing transverse displacement. So let me just take like a small element. It is undergoing transverse displacement, which is out of plane. So let's call this W. And it is also undergoing in-plane displacements u and v in the direction x and y, which is in the in-plane direction that we have already considered, right, before. So therefore, we can write the strains in the system or in this little element as epsilon xx is equal to partial derivative of u with respect to y, u with respect to x, to be given as minus z, second derivative of w with respect to x. Now, so you can actually derive this quite easily or look into a good solid mechanics book to get to this derivation, but this is what you can relate to when you have also an out of plane displacement coupled with an in plane displacement. So you have then here minus z d square w d y square, and finally you have xy to be equal to partial derivative of u with respect to y plus partial derivative of v with respect to x to be equal to minus 2 times z d square w, dou square w, dou x, dou y, which are all partial derivatives. So you see that it's very clear that the transverse displacement w is a function of x and y is enough actually to describe the entire system. Okay. You can also derive all other relations. You can derive the moment relations and the stress strain relations given the moment, etc. And you can go on and describe the entire bending plate theory just by making use of these dependencies. Okay. And of course, if you have a rotation, then it is a derivative or partial derivative of this out of plane displacement W that you have already seen in the case of a beam element which has transverse displacement and rotation at its nodes. So this is in general how we will describe a bending or standard plate theory which is going to be under bending. So now we know what the strains look like. There are forces and moments that cause these kind of stresses to arise, which are of course then a relation of this strain. In the following video, we will start discussing about the triangular plate bending element, particularly in terms of finite element analysis.